In this video, we're going to talk about manipulating equilibrium constants and how we can change them from a forward to a reverse reaction and look at all that. So let's consider the following reaction. We have nitrogen gas plus 3 hydrogen gas in equilibrium with 2 NH3 gas. And at 127 degrees Celsius, the equilibrium concentrations are 3.1 times 10 to the minus 2 for NH3, 3.1 times 10 to the minus 3 for hydrogen, and 8.5 times 10 to the minus 1 for the nitrogen. So first we're going to calculate Kc. And to set up the Kc expression, it's going to be the concentration of the products, and NH3 is going to be squared in this case, divided by the concentration of the reactants. So that's going to be the concentration of N2 times the concentration of H2 to the third power. If we plug the numbers in for this, we have 3.1 times 10 to the minus 2, that quantity squared, divided by 8.5 times 10 to the minus 1 times 3.1 times 10 to the minus 3, and that's going to be raised to the third power. If we multiply this out, we can determine Kc to be 3.8 times 10 to the fourth molar to the minus 2. So now what happens if we asked for the Kc in the reverse direction? So what is the Kc in the reverse direction, or for the reverse reaction? So if we think about this for a second now, we have to rewrite this equilibrium, and it's 2NH3 as a gas in equilibrium with N2 as a gas plus 3H2 as a gas. So this Kc expression, we're going to call Kc prime for the reverse reaction, is going to be the concentration of N2 times the concentration of H2 to the third power divided by the concentration of NH3, that quantity squared. Notice that for this particular reaction, we have the initial reactants divided by the products. So it's simply the reciprocal of our initial Kc. So Kc prime is going to equal 1 over our initial Kc. Okay, so we can take that 3.8 times 10 to the fourth molar to the minus 2 and say 1 over that, and we're going to get 2.6 times 10 to the minus 5 molar squared. Now notice when we're combining these, when we're comparing these, they're both telling us the same thing. This first Kc right here, 3.8 times 10 to the fourth, is going to tell us that this favors the products. And the products in this case is NH3. If we now look at the 2.6 times 10 to the minus 5, this is a small k, so this is going to tell us that this favors reactants. The reactant in this particular expression is also going to be NH3. So regardless of which K we look at, it's basically telling us that NH3 is going to be favored in this particular reaction. Okay? So what happens now if we ask for the Kc for the following reaction? So what is the Kc for 2N2 as a gas plus 6H2 gas in equilibrium with 4NH3 gas? So what we've done here from our initial reaction down to this one is we've doubled the quantities of each. So we're going to call this Kc double prime. That's going to equal the concentration of NH3 to the fourth power divided by the concentration of N2, that quantity squared, times H2 to the 6th power. And notice that, and remember when we multiply exponents, we add them together. And notice how we can compare Kc to Kc double prime. So Kc double prime is going to equal Kc, that quantity squared. And this squared comes from doubling the coefficients. So if we wanted to calculate Kc double prime, we simply take our Kc, which is 3.8 times 10 to the 4th, and we square that. And that will give us 1.4 times 10 to the 9th. Lastly, we can manipulate the equations kind of however we would like. So what is Kc for? And we're going to give this reaction. We have NH3 gas in equilibrium with 1/2 N2 gas plus 3/2 H2 gas. And we're going to call this Kc triple prime to indicate that it's different from the rest of these. So here we've reversed the reaction and we've taken everything in half. Okay, so we're doing both of these things. So when we reverse a reaction, it's going to be 1 over Kc. And in addition, since we've decreased everything by a factor of 1/2, we need to raise it to that power. So here Kc triple prime is going to be 1 over the Kc to the 1/2 power. And if we plug in the 3.8 times 10 to the 4 in for Kc here, we'll get 5.1 times 10 to the minus 3. So this video here is shown to emphasize how we can manipulate equilibrium constants, and kind of it shows how equilibrium are going to be manipulated. And one of the things I want to point out here, and we'll come back to this later in the chapter, is that an equilibrium is great to a chemist because that means we can manipulate this and we can either shift it forward or shift it back. So this is an indication and kind of a glimpse into the fact that we're going to be able to manipulate equilibrium to either force them to go to products or force them to go to reactants, depending on which practical application we're trying to